Assalamu alaikum. As there was a technical glitch this morning that I could not record the lecture, so I'm trying to record it offline, and I apologize again for the technical issue that happened this morning. So as a quick review for the last lecture, we started talking about the pure Aloha protocol. And as we discussed in today's class, that we start the transmission of one single frame by setting the k value to 0, and then we send the frame and we wait for the acknowledgement, which indicates that whether or not we have a collision. So if the acknowledgement has been received, so we reach the success stage. Otherwise, we increment the k value by 1, and we perform the back-off procedure. As we said, that the back-off procedure here is performed by generating a random number. So each node will generate a random number which is in the range of from 0 all the way to 2 to the power k minus 1. So assuming that k is 2, so 2 to the k to the power k is 4. So the range of values for k is from 0 all the way to 3. So 0, 1, 2, and 3. So each node will perform a random number generation, and will calculate a random number from 0 to 3, and depending on this number, the node will have to wait for a time which is multiples of k. The calculation of k, as this example explains, so first we calculate the propagation time. The propagation time here is calculates the time that the signal arrives, or the signal transmits from the beginning all the way to the end of the cable, and then each node will independently generate a random number using the k parameter, and calculates the range of numbers. So for example, if k is 1, the range will be 0 and 1. So each node will generate a random number, whether 0 or 1, and depending on that, the node will, so assuming that if we have the propagation time is 2 milliseconds, so the node will either wait for 0 millisecond or 2 milliseconds. So each node will generate a random number. If the random number is 0, then the node will transmit right away. If the random number is 1, then the node will wait for 2 milliseconds. K is equal to 2, then the range will become 0, 1, 2, and 3. So each node will generate a random number within this range. If the random number is 0, then the node will not wait for any time, and it will start transmitting right away. If the random number is 1, then the node will have to wait for 1 propagation time. If the number generated is 2, then the node will have to wait for double the propagation time, and so on. So when k is equal to 3, the range becomes a 0, 1, 2, all the way to 7, which is 2 to the power k minus 1. And also we have to be aware of the fact that the maximum value for k is 10. So if k is more than 10, we keep it at 10. So 10, the range becomes from 0 all the way to 1023. From 0 to 1023. So because 2 to the power 10 is 1024. So the vulnerable time is a very important parameter for the pure Aloha network, and to calculate that, we imagine that if we have a node A which is trying to send a frame. So node A is trying to send a frame, and we can assume that the frame size is fixed for all the nodes. So this is the beginning of the frame and this is the end of the frame. So if node A sends at time t, the node will spend a time which is equal to the transmission time, which makes this time a t plus t transmission. So the vulnerable time talks about the time within which I should expect the collision might happen at any point in time. So if any node, assuming node B, tries to send within the time duration t to t minus t transmission, so if a node tries to send at any point in time here within this range, the transmission will start at this point and will overlap with the transmission from A, which means that if this is node B, which means that the transmission from node B will overlap with the transmission for node A, which means that there is a collision. So at any point in time within this range, the node will have collision, and at this point in time there will be collision. The only time that there will be no collision is if the node starts at a time which is above t plus the transmission time, above this time here. So if a node transmits after this time, then the collision will not happen, which means that all this time is a vulnerable time, which means that if any node transmits within this range, the collision will happen. So with that said, the propagation time, the vulnerable time is a very important parameter, which in the case of pure Aloha is double the transmission time. So the vulnerable time is equal to double the transmission time, and that's a very important rule that we need to keep in mind. In a pure Aloha network, we have each node can transmit a frame of a length 200 bits, and the medium is shared, and the medium itself has a bandwidth of 200 kilobits per second. So from those two values, we right away can calculate the transmission time. So any node can spend a time which is this value divided by this value, which calculates the amount of transmission time that any node can spend to send a frame of length 200 bits on a medium which is 200 kilobits per second bandwidth. So what is the requirement to make this frame collision free? Which means that we can calculate the vulnerable time, and the vulnerable time is simply double this transmission time. So the average frame transmission time in that case is 200 bits divided by 200 kilobits, which is 1 millisecond. So 1 millisecond came from the fact that 200 divided by 200 times 10 to the power 3, which is 1 times 10 to the power minus 3, which is 1 millisecond. Okay, so so the vulnerable time in that case is simply double that time, which is 2 milliseconds. So the vulnerable time is very important parameter that we use to calculate what we call the throughput. So the throughput here, so this throughput measures the probability of successfully sending one frame to the receiver without having to wait for retransmission. So the throughput as a function is evaluated based on another parameter, which is g. And g here is a very important parameter, which is defined as the average number of successful transmissions per transmission time. Okay, the average number of transmissions for all the nodes in the network per transmission time. Yani within a duration which is the transmission time. So within a duration which is equal to the transmission time, how many transmissions that all the nodes in the network can generate. Assuming that the transmission time is 1 millisecond, so how many nodes send on the average send within 1 millisecond? If the transmission time is 1 nanosecond or 1 microsecond, so how many nodes can on the average send within 1 microsecond, and so on. So this 2, as we can imagine, this 2 here is based on the fact that the vulnerable time is double the transmission time. So this 2 is coming from the double the transmission time. So the throughput is an exponential, is a mix of exponential and linear function based on the parameter g. So we can simply measure the or analyze the throughput. So the throughput will simply become a function of g. So as a function of g, when g is 0, the throughput is 0, and it will increase with a mix of exponential and linear time up to a value, which in that case g equal to half, and we'll talk about why it's half. After that, we will reach the maximum throughput. After this, when g is more than half, the system will start to decay, which indicates that after the value of g equal to half, the system will start to decay in terms of throughput. So the throughput will decrease, not increase. And when the value of g is low, the throughput will increase, which makes sense, because when the value of g is low, this means that the load on the network is low, so the probability of collision will be low. So the probability of sending packets successfully without having any collision will be higher. So any transmission that we will do, it will go through. That's why the throughput increases. After the value of g equal to 1/2, the load on the network starts to grow to the extent that we will have more and more collisions. Okay, and the more collisions we will have, the more that the throughput will decay. And the throughput will decay against g exponentially as we can see. So to get the value of g that maximizes the throughput, we can simply get the derivative of s with respect to g. So the derivative of s with respect to g equals to, we have two functions, exponential function and linear function. So we assume this is f1 and f2. So the derivative of multiplication of two functions is the derivative of, so we keep the function f1 and we get the derivative of the second function f2, which is in that case minus 2 e to the power minus 2g, plus we get the derivative of the first function g here multiplied by the function f2. So in that case the derivative of g is 1, and the other function is e to the power minus 2g. So this derivative is equal to 0, which means that if we can simply multiply by e to the power 2g, which take this away. So we will have minus 2g plus 1 equals to 0, which means that g is equal to 1 over 2. And S maximum, in that case, the maximum S is simply S max is half e to the power minus 1, which is around 0.184 or 18%, or 18.4%. Okay, so this is the efficiency of the system, or the maximum throughput that we can get from a pure Aloha system. A very simple example. A pure Aloha network that has a frame rate of 200 bits. I think we stopped here, so we can simply stop here and continue next time. So we started talking about the carrier sense multiple access last time, and we said that if any node on the shared medium wants to send data here, the data propagates across the cable, and the different nodes can listen to it at different times. So there is a time difference based on which each node can listen to the data transmitted from A. Therefore, we said that the vulnerable time, unlike the Aloha and salted Aloha, the vulnerable time is the propagation time. The vulnerable time here is the propagation time. So based on this, three policies for the persistence of each node trying to access the medium, and the first one is the one persistent and the non-persistent, where the nodes can wait different duration of time before they sense the channel and figure out whether they are idle or not, and the combination of both, which is what we call p-persistence. So these policies have this flow chart. So this is the one persistent, where a node continuously senses the continuously. It uses a very, very short frequency or duration, and it senses the channel continuously until it finds that the channel is idle. Then it accesses the channel with the probability of 1. It accesses the channel right away, immediately, without waiting for anything. The non-persistent, the node always waits for a certain time before it senses the channel again. And if it finds that the channel is busy, then it waits some time and it keeps looping until the channel is idle. So there is a chance that the channel was idle and you did not figure out that the channel is idle until this wait time is finished, right? Which means that you may actually lose the opportunity of accessing that channel. However, this node tends to have more efficiency and more throughput than this node, and this is because of the fact that this method does not try to avoid any collision. So you sense, and then you start sending immediately, which means that there is a high probability of collision. Whereas this, if the time is chosen correctly, the nodes will sense the channel at different times, so collision will be avoided in this policy more efficiently. And this one, the P persistence, seems to have a combination between the two. So the node will sense the channel continuously or using the wait time. And if the channel is idle, the A on A, the node does not try to send right away. Okay? The node will generate a random number, which is what we call the P persistent. This P is a parameter, is a random number, so the node generates a random number. If this random number is less than P, then the node is allowed to send. If this random number is more than P, this means that it's like you flip a coin and the coin says that you should not transmit. When I should not transmit, then I'll have to wait. Similar to the non-persistent case. You will have to wait for a certain time and then you check again. Okay? So these are the three possible policies, and we will discuss these policies again. So based on that, the space-time diagram, we talked about the space-time diagram before, and this space-time diagram here shows when the collision happens. So if a node A wants to transmit on the medium at time t1, it senses that it uses one of the persistence policies, whether it's one persistence or non-persistence or P persistence. Then it finds that the channel is idle. Based on the persistence policy, it accesses the channel. So now at T1, the node accesses the channel. Okay? As we said before, node B will sense that there is a transmission on the medium at this point in time. Okay? And node C will not sense that there is a transmission on the medium until this time, which is P3. So before that time, node C does not realize that there is a transmission happening from A. Okay? So assuming that before this time, at time T2, node C performs the persistence policy, and then it finds that the channel is idle or busy? Idle. So at this time, node C knows that the channel is idle. So it tries to access the channel, okay, assuming one persistence. So it tries to access the channel, and it sends the first bit of the frame. Okay? Then, theoretically speaking, the first time that the collision will actually physically happen is here. Because this is the first bit of the frame sent from C. This is the first bit from A. And they will overlap at this point in time. So collision physically occurs here. Okay? The collision occurs at this point. So if there is a node here, it will be able to detect the collision for the first time. That's why it's called the space-time diagram, because the space has a meaning and the time has a meaning. The space, the location of the nodes, has certain significance, and the time as well has significance. This is very important. So the collision occurs the first time here, but node C will figure out that there is a collision at this point, because node C, of course, listens to its own signal. It knows that it is transmitting, and here it will be able to listen to the transmission happening from A. So node C will be able to detect the collision here, which in the time sequence is after this time. That's why we say that if there is a node here, it will be able to detect the collision for the first time. Okay? So node C will detect that there is a collision here. Node A will not detect the collision until T4. Okay? So there is now a duration T1 to T4, and there is a duration T2 to T8 to T3. What is the significance of this duration and this time duration? This is very, very important now. So imagine if node C starts to transmit at time T2. Okay? And imagine that it tries to send a frame which is very short. Very, very short. And it finishes the transmission of the frame at this point. Before it detects that B is sending. What will happen? What will node C do in that case? The frame is very short and it tries to send a frame. So it finishes sending the frame before it realizes that B is actually transmitting. Will it recognize this situation as a collision? No. So C will not realize that there was a collision. طيب السؤال الثاني. Did the collision actually happen? ليه؟ Yeah, because it actually happened here. There is some kind of overlap. Even if the frame is very short, there is an overlap. However, C will not be able to detect it because the frame is too short. So, this is a very dangerous situation that even though the collision happened, but C will not recognize this as a collision. And this is a very dangerous situation. Okay? So to illustrate this, show the whole frame. So in the previous diagram, we showed only the first bit of transmission from A and from C. Now we show the whole frame. So now C will start transmitting here, and we'll realize that A is sending at this point. Okay, so we assume that each node tries to transmit. It continuously senses the channel even during transmission, and this is very important. Okay, so the node sends and at the same time senses the channel during the entire transmission. Why? Because it has to recognize if there was a collision. Because if there was a collision, it should abort the transmission. And that's what C here did. So C started to transmit at this point, okay, and it keeps transmitting the bits one by one. It spends a time, which is the transmission time. But before the end of the transmission time, assuming that the frame length is considerably large, okay, at this point in time, it realized that A is transmitting. What will it do? It will abort. So here, at this point in time, C detects the collision and aborts the transmission. So when the collision happens, the node will not complete the transmission. The node actually aborts the transmission in the middle. That's why we say it's important for each node to keep sensing the channel even during its own transmission.
So here we're using the P persistent?
Regardless of whatever method. The P persistent or non-persistent or one persistent is used to detect or to decide whether or not you should access the channel now. What we are talking about here is after the fact that node C has chosen to access the channel. Okay? When node C accesses the channel, it will keep transmitting the frame during the entire transmission time. So hopefully this transmission time is long enough, okay, that if there is any collision that will happen, node C will be able to detect it. And this is
the transmission time, which is from T1 to T4?
from T of the transmission time for C is from T2 to some time here, depending on the frame length. I did not tell you what the frame length is. So if this transmission time is short, like until here, right before the C detects that there is a transmission from A, this is a very dangerous situation, because C will decide, okay, I finished transmission, okay, and node A is transmitting now. That's fine, because I finished transmission. But it will not recognize that this is a collision. So it will continue on transmitting other frames, and this frame it will consider that it's a transmitted successfully. It's very bad.
Why is dangerous if C already has been transmitted?
Because C has finished transmission. So during the entire transmission time, C did not detect that there was a collision.
So there is collision.
There is a collision, but happened in the space-wise, it happened somewhere else. But in order for C to realize that it actually happened, okay, there was some time difference. It actually realized that the detection happened, the collision happened after it finished the transmission of the frame. So for C, as far as C is concerned, everything was fine.
Because A transmitted at T1, right?
Right. But it reached C when? At T4, at T3. So it reached C at T3. And C started to transmit at T2. Right? And it finished transmission before T3. So everything's fine. For C, everything is fine, even though the collision has actually happened, because the collision happened at the very first bit here.
So A will detect the collision and
Yeah, so here, this example talks about the fact that if the frame length is considerably large, okay, C will spend time for transmitting the frame, which is more than the time it needs to detect that there was a collision. And that's good, because then C will detect that there is a collision here before it finishes transmitting the frame. And at this point in time, at T3, it will abort transmitting the frame. It's like it's sending bit by bit, and then it cuts out the transmission. It sends the signal, the analog signal, and then it cuts out the transmission. Same thing, A will detect the collision at time T4. So A will abort the transmission at T4. So the abortion time is different for each node. Just the fact that C has aborted the transmission at T3 doesn't mean that A will abort the transmission at T3. It's different based on when each node detected that there was a collision. And this depends on both time and space.
in this case, both nodes will abort the transmission.
Sorry?
In this case, both nodes will abort the transmission.
Right. And this is graceful. This is good. So at least if there was a collision, all nodes will detect that there is a collision gracefully. And they will abort the transmission, which means that this frame will be retransmitted. Because if I finish transmission, the frame is discarded from the buffer. I consider the frame is done, I continue to the next frame. And this would be a wrong decision. This would be very bad, right? So the condition for this to happen gracefully is the fact that this transmission time would be long enough. Because if it's very short, I will finish transmitting the frame prematurely before I detect that there was a collision. Okay?
The detection of collision happens when the node is sensing each other.
Right. When each node, when any node starts to transmit the frame, it continuously sensing the channel, it continuously senses the channel during the transmission. During the entire transmission. Okay, so in order to calculate the worst case, so let's say that we want to calculate the worst case. Okay, so I will try to even though my drawing will not be that accurate, but the worst case would be that node A here is sending a frame, and node A is sending the frame at the beginning of the cable, at the beginning of the shared medium, and node C is at the end of the shared medium. Okay, so node A will start transmitting the frame. So node C will detect that A is transmitting. So this is T1. Node C will detect that there is a transmission at time at time T2. So this is a T2 minus T1. Okay. Be aware now that during this time, مفيش حد يديك أي feedback عن أي. Did you try to see the lecture?
Yes.
Okay. It's good.